Perfect.
Yes, so thank you for the opportunity to chat to you today about renewable energy. In the beginning, let's say about 10 or 15 years ago, it was actually quite a big question. What is a PV panel? What is wind? So is a PV panel something that warms my water? No, that's a solar water heater. These sort of questions have now hopefully been answered mostly. And now most audiences are wondering about how do you integrate, how do you take a lot of renewable power and actually put it onto our power system? And I want to just explore that a little bit. We're in a very interesting stage in South Africa. So yeah, this is the title of my presentation, Integration of Renewable Sources onto the South African Electricity System, Opportunities and the Risks. Right, so we're all aware of load shedding. All engineers like problems. So we normally start our storylines with problems as well. And as you can see clearly on this graph, the red bit here, Peter Jordan shared this, or he shared this in Business Tech. And I think it's quite a nice graph because it just shows that already by May this year, we've exceeded the amount of accumulated blackout times compared to 2022 of load shedding. So load shedding is definitely an issue in South Africa. If you then read more newspapers and if you read policy documents of South Africa, you will find that South African policy makers do think that renewable energies will be a part of the solution to fix both this load shedding and more in general, taking us into a green future. Whether you agree with it or not, it is a policy document. The IRP 2019 is the last one that was published. And that actually predicts, if you look on the y-axis here, that we will build more than a Kuiper nuclear power station's worth of capacity every year, just with wind and PV and solar PV, and then with some batteries once in a while. Now, there's been a more updated policy document called, if you can call it a policy document, but Eskom published a transmission development plan, TDP, and the latest one shows a slightly different increase in renewables, but you can see the trend is still very clear. We're moving into a future with a lot of renewables connected to our national grid, to such an extent that by 2032, coal, which is currently supplying more than 80% of our energy, will actually go down in terms of capacity to 29%, and in terms of energy, I think to about 48% of our total energy. So you can see there's a lot of changes happening. Okay. What we are also seeing is a incredible focus on behind-the-meter solar PV. It's strongly incentivized. If you look at what our president said and Treasury then implemented in terms of there's tax incentives from SARS if you put solar PV on your roof. There's all sort of encouragement from politicians that we put it on our roofs, and there's even a way in which we can loan money or borrow money to actually fund all of this at a preferential rate, with Treasury standing in for the risk associated with this. And what this has led to was a significant increase in what we call behind-the-meter solar. Now, behind-the-meter solar compared to, it's basically between you and your utility, there's a meter which says how much you use, and then behind the meter is on the customer side of the meter. We put a lot of solar PV on our roofs. And you can see this. These are very estimate numbers. But if you look from 2014 to 2023, let me see if I can get my pointer, then you can see more clearly. There's a pen. Yep. You can see here in 2023, there's an estimate that there's about 2.3, these numbers might be a little bit wrong, but around 2.3 gigawatts of formal PV. Photovoltaics that has now gone through the whole REIPPP process, and that's now on our grid. And then behind the meter solar is 4.4 gigawatts currently. That's the current estimate from Eskom, what we are expecting. to be behind the meter. That's sort of invisible, but very much that's the PV on your roof, the PV on shopping malls' roofs, mines installing PV, etc. Look at that. That's almost double
Wow.
from what it has been. Just what's happening in the formal industry. So this thing is really booming, and it's a very inexact science. Sorry, it's behind the meter, not BHM. But it's definitely showing that look at this curve. It's doubling every year. So if this trend continues, we'll have a massive amount of behind the meter PV sitting on our network. The challenge with behind the meter PV I'll get to, but the main thing is it's not controllable. It's not visible. The system operator can't see it and they can't control it, but we'll get to that. Okay, so will behind the PV or behind the meter solar PV then solve load shedding, or will renewables solve it? Let's have a look at what happened in other countries. So I asked a student of mine, a brilliant guy called Ndamarero. He did his PhD and is unfortunately now in Ireland working for the system operator there. But he did a very interesting literature review looking at a lot of countries internationally and their growth or their journey from 0% share of renewables on their network all the way to 100%. Now, there's no 100% renewables country that I know of yet, but that whole transition showed us that as you increase your photovoltaics and your wind, mostly on your network, you'll start getting constrained transmission. So your electricity grid will not be capable of actually handling all the power that's flowing through it, so it would need to be increased. Then once you get to about 20% share of renewables, then we see in all the countries, China, Germany, Denmark, America, we're starting to get to constrained flexibility. Now, flexibility means where it's like you've been flexible or not. If you're really stiff and you can't bend, the same way if you have a very stiff and unflexible network, it can't really respond if there's a quick change. Let's say all the wind blows very strongly and then 5 hours later there's no wind. Your system must be able to respond to these changes. And the same with your demand. Might be all your electric vehicles are all charging at 6 o'clock in the evening, but at 5 o'clock they were nothing because everyone was still driving them home. And then we get the constraint inertia, which I'll not bother with at the moment because that's in the future. But at the moment already, 2022, 2023, we're sitting at about 13% of our renewable energy in terms of annual energy. So that's electricity generation. So we're already sitting in a constrained transmission area. So in theory, we should also be experiencing it. And in 2032, if we build what this policy documents or the various policy documents say we will build, we're actually sitting close to 50%. So we're now moving very solidly into the constrained flexibility area. But I'll go into more details of that later on. But basically, no, renewables will not solve load shedding on its own. We need to actually have a full sort of approach, a much more considered approach, which is then the focus of my presentation. I just want to show this graph as well. With the what I call hosting capacity constraints, which is this grid that doesn't have enough capacity, and the flexibility, which we've also seen, these two are definitely problems which we now need to consider. Another thing that's happened with a boom in renewables integrated into the grid is that the financial viability of many utilities just went seriously south. If you look at these two, these are the biggest utilities in Germany at that stage. Between 2009 and 2015, what happened to their annual net results? That was in the time that solar PV was really being added aggressively onto the German network. And if your main product that you are selling is energy, and now your customers are putting their own energy generators on their own roofs, what's going to happen to your revenue? It's actually going to be crashing. And this is exactly what Germany experienced as well. So that's the third aspect that I would like to chat about today and just maybe explore a little bit more in this primary question of mine of renewable energy integration. There's opportunities and there's obviously risks. And I just want to explore these a little bit more. So let's then start with financial viability. So again, in the media, there's a lot of talk about municipal revenue that would be at risk with this booming solar. There might be a lot of talk about Eskom's death spiral, etc. So there's definitely an awareness forming in South Africa that all is not well in the utility space if we continue with business as usual. And I think everyone is now on board with that message. Let's have a look at a typical utility, a typical municipality. Let's say the municipality of, in my case, Stellenbosch or City Power or someone. It's a balancing act for them. So if a lot of their customers put photovoltaics on their roof, sure, they will have a reduction in revenue because they will sell less power because the customers are now generating their own energy, correct? That means a reduction in the same sales volumes. And then, heaven forbid, but you need to actually pay for the PV that's fed into your grid as well. So all the municipal managers might be very unhappy about this shocking experience. But what you must also take into account is that if there's a lot of photovoltaics on your network, you can actually decrease your cost of electricity supply. You can do it through, firstly, a reduction in your bulk power purchase because the municipality buy their electricity from Eskom. And the more customers are self-generating, and actually the more the municipality is buying from them, the less they have to buy from Eskom. So there's a reduction. That's at least something where you're saving. There's also a reduction in technical losses, which can in certain cases be quite substantial. What is meant by that is if you have a long piece of wire between your generator and your demand, there will be losses. You know, the wire heats up and there's a lot of electricity lost, which you can't bill the customers. So you as the municipality or the utility needs to take that loss. So that will be reduced if your customer is generating on their own roof, or if your supply that you buy to sell to the person next door would be from the customer that is right next to that person. And lastly, cheaper electricity to on-sell, in the sense of if you can buy fed-in power from PV. So all the PV that is on the roof of a residential house or a shopping mall that's not been used, that is now pushed back into the network. If it costs less for that power than it costs for Eskom, then obviously there might be some business model as well. Now, this is not much, but it does actually balance a little bit. So another student of mine, Josh Dippenaar, is working very, very closely with municipalities. And he did quite an interesting study where he looked at three municipalities that had very different strategies on how to deal with renewable energy and their erosion of revenue. The first utility just did nothing. So if you look at the picture here, the domestic non-distributed generating customers, so normal people without PV, would pay 2 rands per kilowatt hour for the energy. And these people, if they now put PV on their roofs, would pay 2 rand for the energy. And if they export, because they have these old mechanical wheel meters, they would actually just get 2 rands per kilowatt hour as well. So this is amazing for the person putting the PV on their roof, because it's really financially viable, because you get for every kilowatt hour that you generate, you actually get 2 rands. Wow. It's not very amazing for the utility. If I look at this graph, percentage of customers with distributed generation, so from 1% to 20%, the more people installing photovoltaics on your network, your municipal network, the more your revenue falls. So you have actually quite a problem once you get to 20% penetration of renewables. Compared to utility 2, introduced fixed charges to offset these reduced sales. So they were basically saying, right, if you don't have PV, you pay 1.90 rand per kilowatt hour. If you have PV, you still pay R1.90 per kilowatt hour, but I'm also going to ask you another 380 rands fixed fee per month, whether you use electricity or not. That is just to offset my revenue loss. And I'm basically going to give you almost nothing for your generation that you push back into the grid. Now, this is wonderful for the utility. And you can see that this utility is actually making money. The more PV owners are installed, more PV panels are installed on the network, the more money this utility is making. Right, so that's the second case. And then the third case is a balanced approach where the utility basically incentivizes distributed generation excess feed-in by having quite a high fixed fee to cover all their expenses, which happens, you know, whether you use electricity or not, all the buckies, all the engineers, all the supplies that need to be kept, etc. Then you have an energy tariff when you buy, but you have quite a good tariff when you sell as well. Now, that utility is breaking even by carefully deciding on their pricing structure for their tariffs. They have the ability to not be impacted negatively by the revenue. But that's just one side of the party. What I'm saying here is sustainable transactions, per definition, i.e. transactions that will allow you to do business again with the other party, are transactions where both parties win. So here we can see the municipalities either losing, breaking even, or winning. Let's have a look at what happens to your customer that actually paid a lot of capital to put that PV on their roof, and now they actually have to pay it back by either saving on their electricity bill or actually making some money by pushing electricity back in. And you can see the guy that installed here with a illegal system with the meter just running backwards, you can get your payback in maybe 5 years. I think it's even better if you start including inflation and all sort of tariff increases. But roughly a customer payback of 5 years, it's a no-brainer. Everyone is going to put PV on their roofs if they have a payback of 3 or 5 years. The customer that is heavily penalized for putting PV on will do one of two things. Either that customer will try and stay illegal for as long as possible, which is not a great idea, but that's the consequences, I think, from a very badly designed tariff. Or if they become legal, all of a sudden it doesn't really make sense for them to put PV on their roof because they get a 21-year payback. I'll rather put my money in the bank and buy a diesel generator. And then the third option, which is the interesting one, is what I would say a relative win-win situation where the utility is breaking even. And in this case, the customer payback period is roughly 10 years. I would say 7 to 10 years. So that is now borderline financially viable decision. Remember, PV panels very easily last for 15, 20 years with not a massive reduction in generation. So actually, this is something where there's a win-win. So the point, actually, the key message in this first discussion or the first point on financial viability, I feel fair and responsive, specifically responsive, because if tariffs take 5 years to change, in that 5 years, the municipality can go under, or the incentivization signals would be totally wrong, sending out a signal of, listen, guys, everyone just put PV on their roofs, which might not be necessarily the right signal. So accurate and fair and responsive electricity pricing design is crucial, I think. That's one of the first things that we should focus on as a country, I think. Now, secondly, moving to our second problem, which is this hosting capacity constraints or the constraints of this electricity grid. Why all of a sudden is there this constraint? I mean, the electricity grid was, well, sort of working fine previously. With renewable energy, there's a very distinct shift from a central to a distributed mindset. Central, what I mean by that is imagine your street. So at the end of your street, you have your little box, your transformer, where the electricity is supplied into from your utility. And then there's a lot of wires that go to all the houses in the street. Now, traditionally, that was a very easy system to design. You just draw a cable and you know that the cable will actually have always a current flow towards the house. nothing's pushing back. You'll always be using electricity. So it's a one-directional flow, and you can imagine the central being central generation, and then you just use it at the end. Compared to the new paradigm is totally different. In your street, I might have just PV on my roof. You might just have an electric vehicle, which is a battery. This guy might have a load shedding battery and some PV. This one has all three of them. And the flow of power is definitely not straight. It's not central. It's totally distributed, and it's very difficult to predict. On a system level, if you look at South Africa, about 80% of our capacity at the moment comes from coal, and that all sits here in Mpumalanga in the north of the country. And then there's long lines that take it to the south and to the east and to the west. And what this means is that's very much the central paradigm when it's just coal power stations, but very much distributed once you now have renewable energy popping up all over the place. And that's definitely not in this area. Renewables is, there's all the sun is over here, and all the wind is maybe here in the Eastern and the Western Cape mostly. So it's definitely a problem that we have as South Africa as well in our power system. And it's very clearly illustrated if you look at Eskom's transmission generation connection capacity assessment for 2024, where they're basically saying, don't even think about trying to connect anything in the Northern Cape to our transmission network, because we actually just don't have space. It's full. The Western Cape and the Eastern Cape, they have some numbers still, but that's already in any case allocated. So they're all also basically full. So all the places where the sunshine and the wind blows, there's no space to actually put renewables onto the network, which is a bit of a challenge, which means we need to solve it and we need to adapt. But the point is then clearly it's not as easy as just change to renewables and let's integrate it into our network. The way to adapt it, there's many opinions. This comes from a study called Better Finance, Better Grid, where they basically estimate that the required grid capacity, additional grid capacity to connect new generation up to 2030, early 2030, is 53 gigawatts. Now that's massive. That's a lot of extra lines. And they say, yes, that can be done by building new infrastructure, but it can also be done by just optimizing the use of the current transmission system. Firstly, by putting your new renewables in areas where there's still lots of space. So let's have a look here. Limpopo has lots of space, Mpumalanga, KZN, Free State, so all the places where there's not much renewables. But that's not necessarily a big issue, because the worst place in South Africa for solar PV, which is Durban, it's in this area. This is a terrible solar radiation numbers. It's still much better than, or it's no, not much better, but it's as good as the best place in Germany. The most sunny place in Germany actually has the same amount of solar as our Durban. So that says that we have really good resource. Wind maybe less so in these areas, but it's definitely worthwhile considering placing your renewables also closer to the load centers. There's less losses, etc. The second option is to also maximize the amount of generation capacity connected at a specific location. So for example, if you already have wind, let's go back to this graph, you already have a wind farm here. So you have the connection already, and the wind mostly blow in the early morning and late evening, let's say, and at night. Then just add a solar panel, solar farm to that same area. And that might actually, now you're utilizing your existing connections much better. Obviously, you need to also be able to curtail, etc. So there's a few technical caveats, but I think that's a way of doing it. But I think the hosting capacity constraints, key messages for me, because I feel passionate about it, there's 4 of these messages. But the first one is we also need more detailed modeling to understand where the bottlenecks are and would be, because it's extremely expensive and very, very long durations to build new grids. You know, you have to buy servitudes through all the farms. You have to put the infrastructure on. So that's a 10-year process at least. The second, so just figure out where it's actually really necessary with proper modeling. That's what that's what's for me very interesting to do. Then optimize the use of current transmission capacity. So we need to think a little bit out of the box there, how to incentivize best use of our current infrastructure. Then what I mean by visibility and control of renewable energy inverters on the network. That has more to do on the distribution network. Imagine in your street, it's really difficult to give rules which says only the first two people in the street must have inverters. You can't really say that, but what you can do is, and I think Australia is definitely moving in that direction, the more you can, as a system operator or as a distribution utility, view all the generators on your network and control them accordingly. For 90% of the time, sure, you can generate, but during these peak hours, 12 o'clock noon or something like that, no, guys, you need to all move down to 80% of your maximum generation. For that, you need to be able to control those inverters, and it's not that difficult anymore. And you need to have visibility on what's actually happening on that network. Is there a problem, and how do we fix it? And all of that is very much coupled to updated regulations. Something that's unregulated is a free-for-all, and then later on, it's normally the case. The regulators are always running behind industry. Industry innovates, and they install, and they play, and they do their thing. And then the regulators come running after with the rule box saying, hey, you can't do this. And that's how it should work. But we do need quick and responsive regulations in this case, especially with a booming market of solar. The quicker you regulate, the less problems you have later of legacy equipment that's not compatible to this whole paradigm that you want to put on that network. Okay, now for my last topic. I want to check my time because I have a little bit of time left. That is system flexibility. So once you have a lot of renewables, you have a lot of uncertainty, and you have a lot of things that can change very quickly, which is not ideal if you have a coal power station on your network. So coal power station, I always compare it to a beer or some sort of box that you braai in. You can't quickly ramp this thing up, make it really hot, and then switch it off basically a few seconds later on. You can't, because there's a big heap of coals, and that coals need to be slowly increased in temperature and decreased. If you shut it down totally, then you have to go and get the blitz again and go and really start this thing up again. That is what is the problem. This is not at all a flexible device, or it has very limited flexibility. Compare that to gas-based generator. That can be more like a blowtorch. You basically switch it on, switch it off. You can vary it very quickly. So that is something that's much more flexible. And you'll also see then in most of the renewable futures, there's always a lot of gas, not so much coal. Compare these two to something like wind or solar PV generation. There it's more like a magnifying glass, where the best you can do is exactly point that or exactly focus that glass, and then you're going to get the maximum heat. But you can very easily move it out of the sun, and that is called curtailment, or you can move your wind turbine out of the wind. So it can actually go up to its maximum potential power generation, but you can very easily curtail it. Curtail meaning move it out of the wind or move it slightly out of the sun. Well, it's done electronically. But basically to at any stage go down. But you can't go up. You can't, if there's just this much sun, generate double its rated capacity. So you can see all generation technologies have very useful, very different attributes. And I don't know if they're all necessary on the network, but the point is you do need a variety of technologies. And definitely for system flexibility, some are much more flexible than others. And what this relates to then, if you have a power system with a lot of coal or a lot of inflexible generation, what we currently have, you, for example, in the evening peak, when your demand actually moves up, let's say from noon to your peak in the evening, that demand, the steepness of that upwards curve can be problematic for your coal generation. If you have a lot of renewables, which make that curve quite steep, you might have to curtail some of your renewables just to make it possible for your coal power station to properly work. The same with what is called minimum generation curtailment, where some of your coal power stations, well, not some, all of them, can't actually operate below a certain percentage, let's say 30% of their maximum rated power. They can't go below that because then their coals die. You can't have a very cold beer. It must have some sort of heat. So for that to happen and to have them still operational for the evening peak that is coming again, you might have to curtail some of your renewables, which is not really an issue. That's part of the future. We'll need to curtail our renewables to get our power station or our power system to run optimally. The problem is who will be curtailed first? Because if you now look at, again, you have CSP, you have wind, you have PV, and then you have behind the meter. Sorry about that, PV. Once you have a massive amount of behind the meter PV, per definition, this behind the meter PV at the moment is not visible and it cannot be controlled. So the system operator, the people that's managing our network, have no idea how much PV at any stage is generating, and they can't switch it off. Compared to all the bigger plants, all the proper REAP PV plants and wind plants, part of their definition is they can be curtailed. The problem is these big plants, these wind and PV plants, are also the most economically viable. They provide the cheapest energy because of their economy of scale. I mean, you can't say that a 3 kilowatt on my roof with a lot of shading and a lot of dirty panels generate as cheap electricity as would a 1 megawatt or 100 megawatt farm in the Karoo somewhere that is properly maintained and cleaned daily, etc. So the problem now is, in terms of curtailment, we might be curtailing the most valuable resources because we have no control over the behind the meter photovoltaics. And a bigger headache for Eskom is they're mostly currently in take or pay contracts, which means they must take all the electricity that is generated. If they don't want it, or if they need to curtail, they still need to pay the plant, which is obviously not ideal. And then for my last slide, key messages in terms of system flexibility. We urgently need an integrated resource plan that is updated to consider this boom in behind the meter PV and the rest of it. But I think the minister said it will be within this week, so I'm quite excited about that. And then in terms of visibility and control of renewable energy inverters, once again, the same sort of thing. The more you can control, the more you can actually have a stable system. Yeah, so that's my story. Thank you very much.